the very first data center simulator, they can simulate every important part of the data center, including the air traveling time and the heat recirculation and temperature per server, per chassis, per data center basis, and the models for the cooling units, the power models for the cooling units, and most importantly, the temperature impact on server powers. So one of the most important motivation of this paper is that previous literature shows very wide range of the power consumption of the fans in the servers. For example, the IBM servers are known to consume more than 30% of the entire server power for their fans, while the Google servers are just 5%. We think that they choose that kind of design optimal point because that is the optimal point for their data centers. For the question from this observation is that why do other parts, I mean the disk or CPU or mainboard, they consume relatively constant power. They shows very uniform distribution among the data centers, but the fans are not. So we conducted a very interesting experiment by our own. We put a server in the controlled area and changed the temperature from the 50 Fahrenheit to 120 Fahrenheit, and measured the power consumption of each component of the server, and figured out that the fans are the only one who shows the power difference by the temperature, by the ambient temperature. We initially thought that when you raise the room temperature, ambient temperature of the server, it is most likely the CPU is going to leak more power, and the DRAMs as well. And we have no idea about what is going to be the power curve for the other parts. So we measured and find that the fans are the only parts who shows the power difference. So we divided the power consumption of the server into two parts, rather constant one, and the fan power. And we modeled the fan power by the inlet temperature of the ambient temperature of the server, and include that model to our simulator. This is very important because later on we find that before showing you the result, some researchers proposed to raise the room temperature of the data center to save the cooling energy, but they largely ignored that the higher room temperature will make fans run faster, and in that case the fans will consume more power than before, which will probably compensate the power gain in the cooling unit. So our simulator is designed to simulate the timing delay of the delivery of cool air, and we identified that we had to have a safety margin up to 6 or 7 degrees Celsius. That means the worst case server, the servers in the top of the rack, have to be under the 7 degrees Celsius under the emergency temperature. So that's the one thing that we identified by using this simulator as one of the big reason we lose cooling efficiency of the data center. And the other thing of the other reason of the cooling efficiency comes from the fact that some servers are operating at relatively higher temperature than some other servers at bottom, because we in the data center layout we supply the cool air from the raised floor and exhaust hot air from the ceilings. So naturally the servers at top is experiencing the the higher inlet air temperature than the servers in the bottom. So in that case, we have to cool down the entire data center up to until every server in the data center is happy. That means actually we are we are lowering the temperature of the data center, spend a lot of cooling energy to accommodate the servers in the top of the racks, while the other servers are actually enjoying the cool summer every day. So that has been identified as one of the big reasons we spend a lot of money for cooling the data center. So in the very last sentence of our paper, we claim that if we have heterogeneous cooling capacity, which means some servers at the top has the emergence temperature a few degrees over the other servers, then we can go easy on cooling the data center and save the cooling, a huge amount of cooling energy and cooling power.